Okay, so U2A2 is types of structures. I find this to be a very boring topic, but I'm going to hit it anyways. There's going to be a part 1 and part 2, so I'm going to try and divide this one up. Well, we'll see how the flow goes. If I'm feeling the flow, I might keep going here. We'll see. Covalent structures. Now, covalent is the biggest category of structures out there. There's greater than 500,000 known to man. These all involve nonmetals. So it's a nonmetal that is bonded to a nonmetal. An example there would be carbon dioxide, which is CO2. Now, the way the bonds form in the CO2 is if I did what's called Lewis dot diagrams for the carbon and the oxygen, it would look like this, and each one of these single electrons can form a bond. If they're partnered up, like over here on the sides of the oxygen, the top of the oxygen, they cannot bond. But the ones that are not partnered, oh, this is awkward. Now I got to go all the way from here around to there. But these are called covalent bonds. Covalent sounds like cooperation, it's sharing. So two electrons share space to make a bond. And this is what we draw our bonds to look like. That's CO2 right there. Now, covalent structures can be gases, liquids, and solids. Here we're only talking about solid structures. So for example, if we had H2O, it's a liquid, but if it gets cold enough, it is a solid. Now, before I start talking about what says En here, electronegativity, I'm going to go over to the ionic things. Where covalent structures, where there's tons of them, more than 500,000, and they're nonmetals bonded to nonmetals. Ionic structures are metals bonded to nonmetals. These are also called salts. So the most common salt that we would think of is NaCl. Let's take a look at what I mean when I say metals and nonmetals. Anything that is to the right of this dividing line right here, if you look closely, you can see it on my periodic table. Anything to the right of that is a nonmetal. Anything to the left of that is a metal. To me, this is the most important dividing line on the periodic table. So things that are covalent are made up of two nonmetals. Things that are ionic are made up of a metal plus a nonmetal. Now, there's one exception on the periodic table. Even though hydrogen is way over here, it belongs here on the periodic table if we talk about reactivity. So it's a gas just like fluorine, chlorine, bromine, and it is a nonmetal. So these ionic structures are solids. They are crystalline. So imagine NaCl and it's a crystal. All of these are crystal solids. Where these could be crystals like sugar. Sugar has carbon, hydrogen, and oxygen, therefore it's covalent. Or they can be amorphous, meaning that they don't have that very specific crystalline structure. Okay, so these are our two major categories right here. These ionics are always solids, well, 99.9% of the time. Covalents can be like gases, like oxygen in the air. They can be liquids like water, or solids like ice. Okay, that's just one example of a solid. Sugar would be another example of a solid. Now, the other way we can tell whether we're going to have a covalent structure or not is by something called electronegativity. So I'll just do a quick run through with you. If we take two structures, let's take methane, for example, and let's take CO2. Electronegativity is your ability to attract electrons. So let's say that carbon is 2.5, and it is 2.5. And think of electronegativity as a scale of 0 to 4, where 4 is very strong. Fluorine is the strongest thing on the periodic table at 4. And like 0.2, 0.3 would be really weak. So think of it as a scale of 0 to 4. Now, hydrogen's 2.1. So you can see carbon and hydrogen are very close together. Their electronegativity difference is 0.4. And what that means is if you're 0.4 or less, you are straight covalent. Now, oxygen is 3.5 and carbon is 2.5. That's 1.0. If you're between 0, this is going to be really important for the testing purposes, I believe. If you're between 0.4 and 1.4, you're called polar covalent. So polar means you have a slight charge. Okay, so the electronegativities are on your periodic table. There will be a key to show you where they are, and all you got to do is subtract the two numbers. Subtract the smallest number from the highest number. If we take water and we have 3.5 for oxygen and 2.1, the difference is 1.4. What this means, so this polar thing I'm talking about, what this means is that the stronger one has a slightly negative charge because it attracts the negative electrons, and the hydrogen has a slightly positive. So molecules that are polar covalent will dissolve in each other, like alcohol will dissolve in water. Things that are covalent, pure covalent, 0.4 difference in electronegativity or less, they will also interact together, like methane and oil. So different types of oils interact well together. Salts are greater than 1.6 in electronegativity. So if we were to take NaCl, then the electronegativity difference would be, I believe it is 3 for chlorine. And if I took sodium, and I'm going to have to look that one up, it's 1.0. That's a 2.0 electronegativity difference. Here's the thing. There's two ways you can look at whether something's covalent or ionic. You can look at the electronegativity difference, or you can say if it's two nonmetals together, it's covalent. Same with ionic. What electronegativity allows us to do is more closely define what we have. So for pure covalent, the electronegativity difference is 0.4 or less. For polar covalent, the electronegativity difference is between 0.4 and 1.6. Now, what's the key here to polar covalent? It means that you're going to have charge separation within the molecule. So you're going to have a negative and positive end to that molecule. Super important in chemistry. We are now going to forget the ionic things, and we're going to look at the covalent things. We're going to look at intermolecular forces. Where something that's ionic is one big crystal, and there's no spaces in between. It's one big molecule. Things that are covalent, let's take propane gas that's in your barbecue. There's one propane, there's another propane, and they can have forces in between them. I'm going to give you some very simple keys. If the molecule only has C's and H's, so the electronegativity difference between the carbons and hydrogens is very low, it's going to have dispersion forces, which means it's going to have weak forces holding it together. Intermolecular forces are forces between the molecules, not within the molecules. All the bonds are covalent, but the forces sort of attracting these molecules are called dispersion. They're very weak. Think of a gas. Think if you could smell gas in the room, the gas will spread out, and it's because these forces are very weak. If a molecule has something other than carbon and hydrogen on it, so let's say it's got an oxygen on it, we now have what's called a dipole or a dipole-dipole. So what you're going to get is you're going to get negative areas of the molecule and positive, and they will attract each other. So this little symbol here just means slight negative, slight positive. Dipoles have stronger forms of attraction. Now, with the dispersion, there's ways that you can increase this attraction. So for example, larger molecules will have more dispersion forces. So fats have dispersion forces, yet they're solids because they have more of those dispersion forces. So here's your look force. If you just have carbon and hydrogen, you've got dispersion. If you've got carbon with something else attached to it, then you've got a dipole. If you have OH groups on anything or NH groups, you are going to have hydrogen bonding. Now, hydrogen bonding is a misnomer. It's not a bond. It's a force holding these molecules together. So it's not really a hydrogen bond, it's a hydrogen force. And these hydrogen forces occur when you have OHs or NHs on molecules. Remember, it can be OHs or NHs. Now, I'm going to teach you something that I probably really shouldn't, but I'm going to say it anyways. If you have an OH on one molecule and an O on the other, you can still have a hydrogen bond. So you just need an OH on one and an O on another. But if you have two OHs, two NHs, an NH and an O, an NH and an N, then you can have hydrogen bonds. But look for that OH or that NH, and that'll tell you have the strongest of the strong. And you're more likely to get a solid with these stronger. So weakest, more likely to be a gas. Next strongest, strongest. And these only go with covalent structures. So these are forces that are found in between covalent structures that attract those covalent structures to each other.